There is a beautiful lecture by Feynman that you can see online. It's a historical lecture on the great conservation principles. And from that one, I learned something important, that what we call laws of nature are essentially general rules that we have been accustomed to consider essential for our modeling of anything related to, of course, natural phenomena. And so this is what I want to talk about. So it's rules of modeling that are possible candidates for laws of nature. And since my time is limited, I'm going to start and focus on what I'm trying to suggest that could be considered the fourth law of thermodynamics, having to do with non-equilibrium. So let me start from an example. Consider a heat transfer problem on a material that is non-isotropic. And, for example, layers of a highly conductive material on like an epoxy of low conduction. And we know that in this case, if you apply a gradient in one direction, you get a heat flux that doesn't follow, doesn't have the same direction. And the two are related linearly, of course, by the conductivity tensor, which, by the way, is symmetric because of Onsager principle. The interpretation of this is that the material, this particular material, which is non-isotropic, feels different directions of heat flux differently. And when I say feels, it's that as if the material really had to decide which direction to pass things along. And because of the non-isotropy, for this material, it is easier to pass things along the highly conductive direction than the low conductive direction. So among all these possibilities, again, if you put yourself in the shoes of the material has to decide where to move or what to do at a given equal cost. So somehow this ellipse represents the cost for the material to transfer heat in these various directions. And if you look at it this way, then you notice that the local entropy production is the scalar product of the flux and the gradient, and so the material will choose among those equally costly fluxes the one that maximizes the scalar product, therefore maximizes the local entropy production. This is for a steady state situation. The same idea applies also for non-equilibrium dynamics. If you consider here a plane where, say, the energy and all the constants of the motion are fixed, and these are the contour levels of the entropy. So this is the maximum entropy state for those given values of the energy and the other conserved properties. And suppose you are here. Now, if your material is isotropic, it feels equal cost to move in all directions. So this is like a circle. If your material is anisotropic, it's easier for it to move in the horizontal direction, for example, here, because that's the layer of higher conductivity than in the vertical direction. And so these two will evolve in time by searching, see, where it is tangent. This is where, among the possible equal cost directions, you get the higher increase in the entropy, and so on. And then you follow this way the trajectory till you get to equilibrium. Now, if you start from the same non-equilibrium state, but for a different material that has a different local perspective on what is the cost of moving, this material will follow a different trajectory. And here I also consider the possibility that as you move, as you change in state, the metric with which the material decides on how to follow steepest entropy ascent can change with state. And then it will get gain to equilibrium along a different path. Onsager theory belongs to the near equilibrium region. And so this metric, when you get near equilibrium, is the Onsager generalized conductivity tensor. Now, this is a particularly simple material and problem with only the transport of energy, but as you know, if you have also transport of charge and diffusion of particles and so on, you get the cross effects and all that. So that's the idea, the geometric idea of what I call steepest entropy ascent. Now, regarding, I'll go back to that in a moment. Now, regarding more basic concepts having to do with the other three laws, energy is the result of the first law. So the fact that the system has energy is a typical thing that we want out of our models of physical reality. We also want entropy, and some people still argue whether entropy is defined or not in equilibrium. I don't want to argue that because I think it has been settled enough in papers by ourselves and also well-known physicists that have picked up more recently. So all I want to remind you is that you can have, for a system, for example, a fluid element. This is energy density, entropy density, and concentrations with the hat, means density, energy per unit volume. So you can draw an energy versus entropy diagram, which is also the cover of our book in 1991. And on this diagram, we can show, for example, the fact that for given energy, a system has many states. Only one of them is a stable equilibrium state. The others are non-equilibrium, and you can be far or near equilibrium. This is the realm of Onsager reciprocity. This is a more open field of research. When you want to do modeling of a system, if you constrain yourself just to the equilibrium, stable equilibrium states, then you have to have a model in which you have a fundamental relation. This is very standard. If you want to model non-equilibrium states, you need additional variables. And so the entropy, the energy, and the concentrations are functions of these variables. I'll call them gamma for today. And of course, your theory must be compatible with the fact that for given values of the constants of the motion, like the energy, there must be one and only one equilibrium state, so you have a fundamental relation in which these additional variables then take are precise functions of those energies and other conserved properties. So what characterizes the different theories of nature that we have is what we choose for gamma. For example, here's the list of state variables of a whole lot of different theories that we adopt. And each one has a formula for entropy, and I don't have time to go into the details here, but you probably recognize your own favorite theory here. The only step I want to do is that whenever there is a probability, I suggest, I prefer that we think of the square root of the probability, so that if you work with square root, then it's easier in your model to keep the non-negativity of the probabilities, because you just have to square a number so it's always positive. Apart from that, when you write the dynamical law for your model, there is always, so to speak, a left-hand side having to do with rate of change of the state or fluxes, so rate of exchange of properties with neighboring fluid elements or neighboring systems. And there is an internal dynamics that is responsible for the irreversibility, the dissipation. And I like to focus on this one. For example, in the quantum, if I have a D-level system, a system with D energy levels, in a very particular subset of states, where the density operator commutes with the Hamiltonian, just to simplify, you can think of probabilities as being the population of the various energy levels of your system. And here's the energy versus entropy diagram for such a system. This is a 7-level system, so there's the blue curve. And for a given energy, you can have different states. For example, this is a pure state in which all the energy is just on one level, the third level. This is the canonical, the Gibbs state, canonically distributed with positive temperature, and that's with can I say, pseudo negative temperature, okay? Just joking because of Henning's talk yesterday. This is a point that represents various possible states that all have the same energy and the same entropy, distributed this way, okay? If instead of several energy levels, you just have a bit, a qubit, 2-level system, then the states map on a unit ball, and so that means this is the block ball. The pure states are on the block sphere, and as you see here, for example, you have constant energy states, and these are the entropy contours. And you can draw various diagrams. For example, I can, instead of doing X, Y, and Z component of the magnetic moment, I could select as an independent variable the entropy. Then I have X, Z, which is also energy, and entropy, and so I get this paraboloid kind of description. And if I project it on the E versus S, this is the E versus S diagram. And that's and this is the constant energy place. So now my concern is how to describe time evolution of a state that would evolve towards equilibrium along the steepest entropy ascent. The idea is that the various laws of evolution can be different depending on your model, but should have a structure in which you have the rate of change of the state is related to a part which accounts for the reversible dynamics and a part which accounts for the dissipative dynamics. And then you apply this equation, and then the system, the key is that the system at every non-equilibrium state must have defined some metric which is the way in which it perceives distances between states. It's the thing that it makes the system decide which direction to move, like in the example we've seen graphically before. So for a given effort in moving, the system will choose the direction of steepest maximal entropy increase, maximal entropy production. Then the problem becomes just Lagrange multiplier optimization and simple mathematics. You can apply, I'm not going to show this, of course, and don't be worried about the number here. I'm not talking about all these slides, they're just for questions later. So here's the result of applying that idea, that you get spiraling motion towards equilibrium, and this motion can be viewed in various points. On this diagram, it's just moving from here to there. A nice aspect of this kind of dynamical model is that you can solve it not only forward in time, but also backwards in time. In other words, it's mathematically reversible, although it describes physical irreversibility differently from other models like the linear Lindblad equation, that if you solve it backwards in time, at a certain stage it will boil out. So my suggestion is that this idea of steepest entropy ascent could be considered as a general principle at the same fashion as stable uniqueness of stable equilibrium states is the general principle that we call a statement of the second law, the Artsopoulos-Kinam statement of the second law. Let me just go back. Now, I'm saying this not because just of our proposal, but because essentially the steepest entropy ascent has been a precursor of several modern theories of non-equilibrium that some of which you have heard and some of which you know, some of which you're working on. And you see here they start, we all started around 1984. Miroslav Gromela was among them. And then we have various other contributions that go in the same direction. Even gradient flows in mathematics, large deviation theory, you'll hear about it, I assume, soon, and also maximal entropy production from the information theory point of view. So the last concept I want to talk about is, well, why then are people talking about minimum entropy production? Is it minimum or maximum? Okay. And I want to clarify this because it is a source of confusion sometimes in the literature. Locally, the system chooses the direction of maximal entropy increase. The theorem on minimum entropy production, which was proved by Glanzorf and Prigogine in 1954, has to do with global. So you have like a control volume of many fluid elements, and you look at the global entropy production. And you have a formal proof that under very wide boundary sets of boundary conditions, the rate of change of the entropy production rate of the overall, so the integral of the overall entropy production over the volume, is negative. It means that you start from a state, it has a certain value, it goes down in time until it reaches either zero, and then that would be equilibrium, or a fixed value, which is steady state, come down. Here is the example. Suppose you take just a simple material, and you impose an unsteady, an initial temperature distribution like that. You compute the integral of the local entropy production. So the local entropy production is steepest entropy ascent, but when you integrate, you get a certain value. If you solve this problem and let it go in time using simple Fourier law, eventually you get to a steady state. In the steady state, the entropy production has halved. Okay? Or, for example, start from here, where you have impose this odd distribution of entropy. So you have an entropy production, then you let it go, it will reach zero. So it will go down until it goes to zero, and that is an equilibrium situation. So there's no contradiction between minimum production theorems and local maximum entropy production. Thank you.
My question. What about in relativistic theories? There is no time, no energy, only energy, pressure, I mean vector, and so what will you do?
I'm not an expert. I don't dare say anything about relativity. And I suppose that one should use the same kind of logic, but I hope you can do it. I'm not able. Sorry, too difficult.
And you have mentioned at temperature, which is the absolute temperature, I imagine that it may be measured probably by means of a Carnot cycle between a non-equilibrium source and an equilibrium one, a non-equilibrium reservoir. What relation have? How do you measure this temperature if it is not through a Carnot engine?
How do you, oh.
Is the meaning of this temperature, because you have said we will have you defined in every state, equilibrium or non-equilibrium, as defined in every state from these choice of gamma variables, and therefore you will have T, and this T probably is the derivative of S with respect to U minus 1. And but the topic is how to measure this temperature.
Okay. Now, there is a distinction that one should make. I think I understand the question, and one has to make a distinction between what is the definition of entropy, which is model independent, and it's something model independent. So you should have a definition that applies to all systems somehow, and then the particular dependence that you impose in your model between the internal variables and the entropy. I mean this formula here. So the various models differ in this one. Then once you have a formula, then it's simple to do the maximization and find the Lagrange multiplier, the beta, and so on, and then you can identify the temperature. Now. Why do you call it temperature? Because it comes out when you ask what are the necessary conditions for mutual equilibrium between systems, okay? And thereby the idea of a thermometer and all that. So you measure on the basis of this theorem that says that the partial derivatives of the entropy, the inverse of the partial derivative of the entropy with respect to energy should be equal between the two systems that are in contact. And so that's the basis for the instruments. And it is a basis that is nice because being independent of the model, you measure something of an object of which you know nothing, using the thermometer. And that's how you build up the properties of that material. That's how you construct the property of that material.
Next question. If I understood you correctly, then the steepest descent makes the shortest path. This is a kind of variation of principle. But how important it is that you have a symmetry in your state space? Must it be symmetric or just must it be non-negative, definite, or whatever?
The fact that it is a metric by definition in geometry, has the symmetry properties. So automatically that will give you near equilibrium, the Onsager reciprocity. It's built in. But it also gives you other symmetries that may emerge far from equilibrium, which are there to be discovered.
Can Thank you.